This is SpaceTime, Series 21, Episode 34. Coming up on SpaceTime, a star stripped naked. The Milky Way's monstrous supermassive black hole may have hidden siblings. And Gaia provides the best map yet made of the Milky Way galaxy. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have finally identified a star which survived the massive explosive death of a companion star in a rare type of supernova. The findings, reported in the Astrophysical Journal, are the culmination of a 17-year study providing the first ever images of a binary companion to a supernova. The study's lead author, Dr. Stuart Ryder from the Australian Astronomical Observatory, says the study provides the most compelling evidence yet that some core collapse supernovae do originate in double star systems. Ryder and colleagues used NASA's Hubble Space Telescope to study the fading afterglow of a massive supernova catalogued as SN2001-IG, which exploded in the year 2001, some 37.5 million light-years away, in the galaxy NGC 7424, located in the southern constellation Grouse the Crane. Astronomers know that the majority of stars, including massive ones, are in multiple star systems, many in binaries. And many of these binary pairs will interact with each other, transferring material from one star to another when their orbits bring them close together. In the case of SN2001-IG, the companion to the supernova's progenitor star had gravitationally been drawing hydrogen off the doomed star's gaseous stellar envelope, the region that transports energy from the star's core to its atmosphere. Millions of years before the primary star went supernova, the companion's actions were already creating an instability in the primary star, causing it to periodically blow off a cocoon and shells of hydrogen gas. SN2001-IG was a rare Type 2b stripped envelope core collapse supernova. This type of supernova is unusual because most, but not all of its hydrogen is already gone prior to the explosion. But exactly how stripped envelope supernovae lose their outer envelopes isn't quite clear. They were originally thought to come from a single progenitor star, with very fast winds that blew away material in the outer stellar envelope. The problem was that when astronomers started looking for the progenitor stars from which this type of supernova was spawned, they couldn't find them for stripped envelope supernovae. Now that was especially bizarre because astronomers always expected that they would be the most massive and brightest progenitor stars, consequently fairly easy to spot. Also, the sheer number of stripped envelope supernovae appear to be far greater than what's predicted for these types of stars. Now, that's led scientists to theorise that many of the progenitor stars must have been from lower mass binary systems, and it was this which they set out to prove. Looking for a binary companion after a supernova explosion is no easy task. Firstly, it needs to be relatively close to Earth for Hubble to be able to see such a faint star. And at 37.5 million light-years, SN2001-IG and its companion are very close to that limit. Within that distance range, not many supernovae go off. In 2002, astronomers were able to pinpoint the precise location of the supernova using the European Southern Observatory's VLT, or Very Large Telescope, in Chile. Then in 2004 they followed up with observations using the Gemini South Telescope, also located in Chile. And it was this observation which provided the first hints of a possible surviving binary companion star to the supernova progenitor. Knowing the exact coordinates, Ryder and colleagues were able to focus Hubble on that location 12 years later as the supernova's glow faded. Using Hubble's resolution and ultraviolet capabilities, the authors were able to find and image the surviving companion. They were able to determine that prior to the supernova event, the orbit of the two stars around each other took about a year. Often, when a primary star explodes in a binary system, the other star is sent flying off in the opposite direction, becoming a runaway star. But when the primary star exploded in this event, it had far less impact on the surviving companion than might be thought. According to Ryder, it's like imagining an avocado pit representing the dense core of the companion star, embedded in a jello dessert representing the star's gaseous envelope. As the shock wave passes through, the jello-like gaseous envelope might temporarily stretch and wobble a bit, but the avocado pit-like dense stellar core would remain intact. Back in 2014, astronomers used Hubble to detect the companion of another Type 2b supernova. It was known as SN1993J. However, they weren't able to capture an image, just a spectrum. In the case of SN2001IG, this is the first time the surviving companion's actually being photographed. Perhaps as many as half of all stripped envelope supernovae have companions. The other half probably lose their outer envelopes through stellar winds. Ryder and colleagues now have the ultimate goal of precisely trying to determine how many supernovae with stripped envelopes have companions. They now plan to look at completely stripped envelope supernovae as well, as opposed to SN2001IG and SN1993J, which reach only about 90% stripped. These completely stripped envelope supernovae don't have much shock interaction with the gas in their surrounding stellar environment, since their outer envelopes were lost long before the star went supernova. And without that shock interaction, they fade much faster. This means the team will only need to wait 2 or 3 years after the supernova event to look for surviving companions. In the future, they also hope to use the new James Webb Space Telescope, when it finally flies, to continue their research. James Webb's now expected to launch on a European Space Agency Ariane 5 rocket from the Kourou spaceport in French Guiana in 2020. Ryder says the research plays an important part in helping science better understand stellar evolution and the role it plays in producing elements allowing planets, and in fact life itself, to exist.
That's right. So the Hubble Space Telescope Time Allocation Committee was kind enough to give us a couple of orbits, which just doesn't sound like a lot of time, but it was really all we needed to take a couple of images, and these 2 different ultraviolet filters. And the fact that we could see it in both of them was a good clue that this was a real object. And by looking at the difference in brightness between the 2 filters, it fit pretty well with our predictions of what type of star we expected to find at that location. And we had evidence as well from the Gemini telescope, for instance, that showed that there was emission due to helium gas at that location and nowhere else in the field.
What's the significance of the helium gas?
The helium that we saw in our Gemini observations, in fact, is consistent with an ongoing shock wave. So we know that star explodes. There's a blast wave that moves outwards through space at speeds typically around 10,000 kilometers per second. And when that blast wave plows up any gas in its vicinity, that creates a shock wave, and it's that shock wave that we detected with the Australia Telescope Compact Array, for instance, at radio wavelengths. But we can also see evidence of that shock at optical wavelengths, in particular this helium line, which we're able to show is attributable to an ongoing shock interaction. Even many, many years after the explosion, that shock wave has slowed down quite a bit because there is more and more material out there to decelerate it, but it hasn't completely run out of puff, and so we still see evidence for that in the presence of this helium feature. Again, that's consistent with this companion star carrying out this stripping activity over many, many orbital cycles, and that gas that it stripped off, a lot of that has slowly dispersed over time, and it's that shock wave is still making its way through that stripped gas even 15, 16 years after the explosion.
You said earlier that the companion star was most likely a blue star. What makes you say that? Is that something to do with the amount of mass that it secreted off the primary star, or is that just simply the size of the star that can withstand a supernova blast?
It's a bit of both, I think. Well, one of the really interesting things that's happened, even since 2001 when the supernova went off and was discovered, colleagues in Europe have been making observations of nearby massive stars, and again I'm talking things that are typically 10 times the mass of our sun or more. And what they're finding is that the majority of these massive stars are not single stars like our sun. They nearly all, not everyone, but more, at least 2/3 of them seem to have a companion star. And that companion star is typically about as massive as the main star. So actually what looks like one super hot massive star may turn out in fact to be 2 slightly less massive hot stars on a close binary orbit. It's just that we can only now begin to be able to separate out those 2 individual stars.
Does that tell us something about the way they formed, if both stars in the binary are similar in mass?
Yeah, it certainly does, but we haven't quite figured out what that exactly, how that relates to the way that stars form, because typically when one core of a star gets going and starts to begin the process of nuclear fusion, it releases so much energy that makes it very, very difficult for any other stars to form in the immediate vicinity. So the fact that clearly you can get not just 1, but 2, and sometimes maybe 3 or 4 stars of a similar mass all forming together suggests that we've clearly a bit more work to do if we're going to properly understand how stars of different masses really come together and get going.
That's Dr. Stuart Ryder from the Australian Astronomical Observatory, and this is SpaceTime. I'm Stuart Gary. Supermassive black holes are among the most powerful objects in the known universe. These monstrous gravity wells, containing millions to billions of times the mass of the Sun, are thought to exist in the centres of most, if not all, galaxies, and play an important part in galactic evolution. Sagittarius A star, the supermassive black hole at the centre of our own Milky Way galaxy, contains about 4.3 million solar masses. Luckily, it's some 26,000 light-years away. But what if it had siblings, invisible monsters similar in size roaming the galaxy, consuming anything that gets too close? Astronomers are now beginning to understand what happens when black holes get the urge to roam through the Milky Way. A new report in the astrophysical journal Letters claims multiple supermassive black holes may be wandering throughout their host galaxies, remaining far from the centre in regions such as the stellar halo, a nearby spherical area of stars and gas that surrounds the main sections of the galaxy. The authors theorise that this phenomenon might be common in galaxies as they interact gravitationally with each other, merging in an expanding universe. As smaller galaxies are cannibalised by more massive ones, their central supermassive black holes would be flung into wide orbits around their new host before eventually being drawn towards the galactic centre of the newly merged galaxy. And the Milky Way would be no exception to this rule. Stellar streams both within our galaxy and coming towards it from surrounding satellite galaxies like the Large and Small Magellanic Clouds and the Sagittarius Dwarf Galaxy are clear evidence of the Milky Way's own galactic mergers. The study's lead author, Michael Trammell from the Yale Centre for Astronomy and Astrophysics, says galaxies with masses similar to the Milky Way are likely to host several supermassive black holes. Trammell and colleagues used a new state-of-the-art cosmological computer simulation called Romulus to predict the dynamics of supermassive black holes within galaxies with better accuracy than previous simulation programs.
Supermassive black holes are sort of a special breed of black holes. They're much more massive than the black holes you're maybe used to hearing about. In the early universe, these black holes are forming in very early forms of galaxies. The traditional picture is that their supermassive black holes will come to the center of the galaxy and merge together. So in this study, we're looking at how supermassive black holes move within their galaxies. If we look at massive galaxies the size of the Milky Way, we find that on average, these galaxies host several supermassive black holes within them, wandering about the galaxy on scales of several thousand light years from the center of the galaxy.
Because these wandering supermassive black holes are expected to exist outside the galactic disk for some time, they're unlikely to accrete lots of gas. And because black holes don't emit light unless they're feeding, they're likely to remain virtually invisible. Trammell says it's extremely unlikely that any wandering supermassive black hole is likely to come close enough to the Sun to have an impact on the Earth or our solar system. In fact, he estimates that a close encounter with one of these invisible monsters would be likely to occur only about once in every 100 billion years or so. Still, the race is now on to find ways of inferring the presence of these invisible monsters through indirect means.
Now that we've discovered gravitational waves and there's a new gravitational wave telescope that will be put in space in the next couple decades, we can really get a clear picture of black holes through time. But in order to learn about them, we need to understand how often and when these sort of mergers might occur.
I'm Stuart Gary. You're listening to SpaceTime. The European Space Agency's Gaia mission has now released the richest star catalogue ever developed. The spacecraft's data set is providing high-precision measurements to nearly 1.7 billion stars, in the process revealing previously unseen details of the Milky Way galaxy. This long-awaited release is based on 22 months of charting the skies. The new data includes positions, distance indications, and motions of more than 1 billion stars, along with high-precision measurements of asteroids within our solar system and more distant stars beyond the Milky Way galaxy. Preliminary analysis of the new data is revealing fine details about the makeup of the Milky Way stellar population and about how stars move, essential information for investigating the formation and evolution of our home galaxy. ESA's Director of Science, Gunther Hassinger, has described the new observations in the Gaia database as redefining the very foundations of astronomy. Gaia was launched back in December 2013 and started science operations the following year. Its first data release, based on just over a year of observations, was published in 2016, containing distances and motions of 2 million stars. The new data release, which covers the period between July the 25th, 2014 and May 23rd, 2016, pins down the positions of nearly 1.7 billion stars, and with much greater precision. In fact, the accuracy of the new measurements makes it possible to separate the parallax of stars from their true movements through the galaxy. Parallax is the apparent shift of foreground objects in relation to background objects in the sky caused by Earth's yearly orbit around the Sun. You get the same effect by looking at your thumb on an outstretched arm in front of you, by alternatively shutting and opening one eye and then the other. By keeping your thumb still, you'll see the background change perspective. The new catalogue lists the parallax and velocities across the sky, also known as proper motion, for more than 1.3 billion stars. From the most accurate parallax measurements, about 10% of the total, astronomers can now directly estimate distances to individual stars. The chairman of the Gaia Data Processing and Analysis Consortium executive, Anthony Brown from Leiden University in the Netherlands, says this second Gaia data release represents a huge leap forward with respect to the Parkos satellite that was Gaia's predecessor and the first space mission for astrometry, which surveyed some 118,000 stars almost 30 years ago. As well as positions, the new database includes brightness information on all surveyed stars and colour measurements of nearly all, plus information on how the brightness and colour of 500,000 variable stars change over time. It also contains the velocities along the line of sight of a subset of 7 million stars, surface temperatures for about 100 million stars, and the effect of interstellar dust on 87 million. Gaia has also observed objects within our solar system. In fact, the second data release includes the positions of more than 14,000 known asteroids, allowing precise determination of their orbits. And it doesn't end there. An even larger asteroid sample set will be compiled for future Gaia releases. Further afield, Gaia has also closed in on the positions of more than 500,000 distant quasars, unusually bright galaxies powered by actively feeding supermassive black holes. Because of their distance and brightness, quasars are used to define a reference frame for the celestial coordinates of all objects in the Gaia catalogue, something that's routinely done in radio astronomy but is now being done for the first time in optical wavelengths. The new Gaia databank has also developed unrivaled new insights into the evolution of stars. That's come through the development of the most detailed Hertzsprung-Russell diagram of stars ever made on the full sky. The Hertzsprung-Russell, or HR diagram, is a fundamental tool to study populations of stars and their evolution based on the relationship between the intrinsic brightness or luminosity of stars and their spectral classification based on colour and surface temperatures. And astronomers are already seeing some interesting trends in the new data, which could be inaugurating a new era of galactic archaeology. The new version of the HR diagram is based on some 4 million stars within 5,000 light-years of the Sun. This includes the signatures of different types of white dwarfs, the corpses of dead Sun-like stars. The new HR data means a differentiation can now be made between those white dwarfs with hydrogen-rich cores and those dominated by helium. Combined with Gaia measurements of star velocities, the diagram enables astronomers to distinguish between various populations of stars of different ages that are located in different regions of the Milky Way, such as the disk and halo, and that formed in different ways. And further scrutiny suggests that the fast-moving stars thought to belong to the galactic halo actually encompasses 2 stellar populations that originated through 2 different star formation scenarios, a finding that's already calling for more detailed investigations. And even in the Sun's own local stellar neighbourhood, a region astronomers thought they knew pretty well, Gaia is revealing some new features. For a subset of stars within a few thousand light-years of the Sun, Gaia has now measured their velocity in all 3 dimensions, revealing patterns in the motions of stars that are orbiting the galaxy at similar speeds. Further studies will confirm whether these patterns are linked to perturbations produced by the galactic bar, a denser concentration of stars in an elongated bulge at the centre of the galaxy, or whether their patterns are caused by the spiral arm architecture of the Milky Way, or possibly even through interactions with smaller galaxies that merged with the Milky Way billions of years ago. Gaia's data has also been used to derive the orbits of 75 globular clusters and 12 dwarf galaxies that evolve around the Milky Way, providing all-important information to study the past evolution of our galaxy and its environment, the gravitational forces that are at play, and the distribution of that elusive dark matter which permeates galaxies and provides the very scaffolding upon which galaxies are formed. You're listening to SpaceTime. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. And you could say it's DNA, but not as we know it. In a world first, scientists have identified a new DNA structure inside living human cells called the intercalculated or eye motif. A report in the journal Nature Chemistry claims researchers with the Garvan Institute and the Universities of New South Wales and Sydney identified the previously unknown structure shaped in a twisted 4-strand knot of DNA that had never before been directly seen in living cells. Deoxyribonucleic acid, or DNA, has captured the public imagination ever since the discovery of its double helix structure by James Watson and Francis Crick in 1953. Comprising the elements hydrogen, oxygen, nitrogen, carbon and phosphorus, DNA is made up of nucleotides, each of which is composed of one of 4 nitrogen-containing nuclear bases, cytosine, guanine, adenine or thymine, as well as a sugar called deoxyribose and a phosphate group. Combined, these provide very precise instructions for how living things are built and how they work. However, it's now known that short stretches of DNA can exist in other shapes, and scientists suspect that these different shapes may play important roles in exactly how and when the DNA code is read. The DNA double helix base pairing always sees adenine linked to thymine, and cytosine always linked with guanine. However, in the knot structure, cytosine on the same strand of DNA bind to each other. Scientists think the comings and goings of the eye motifs helps to switch genes on or off, affecting whether a gene is actively read or not. Well, following last week's news that having 3 cups of coffee a day was actually good for you, comes a new study suggesting that pregnant women should cut out caffeine altogether. The findings, reported in the British Medical Journal, are based on research showing that there may be a link between consuming mid to high levels of caffeine during pregnancy and a risk that your children could gain too much weight in early childhood. Existing guidelines in Australia and New Zealand recommend limiting caffeine intake while pregnant, but the authors of this study are advocating for a complete cold turkey approach. And worse news, the study didn't just target coffee. In fact, none of your favourites were safe. Black tea, caffeinated energy drinks, chocolate milk, sandwich spreads, desserts, cakes, and even candy are all on their hit list. A new study has found that anti-vaccination activists demonstrate similar beliefs about being persecuted as other conspiracy theorists, resulting in their networks becoming virtually immune to any outside influences or facts. The study, by researchers at the Australian National University, examined some 300,000 text comments from around 14,700 individual posts on 6 anti-vaxxer Facebook pages from Australia and North America. Researchers identified similar topics to other conspiracy theorists, including a belief that the government and media underplay and deny the dangers anti-vaxxers believe are caused by vaccinations. They also found that the anti-vaxxers movement may be far less close-knit than previously assumed, with most users appearing to be fairly transient, initially commenting on a few posts and then suddenly disappearing forever. Anti-vax networks were also found to be small-world, meaning that information spreads extremely rapidly throughout each network, and that networks were very resilient to attacks by outsiders or outside influences. Interestingly, there was also a very significant gender skew in the anti-vax movement, with some 3/4 of all anti-vaxxers being female. Well, some good news now, and a new study claims eating dark chocolate could improve your eyesight. Well, maybe. The findings, reported in the Journal of the American Medical Association Ophthalmology, are based on tests on volunteers' eyesight around 2 hours after they've eaten milk chocolate and dark chocolate. The milk chocolate and dark chocolate were each consumed several days apart. While they did find that dark chocolate appeared to give people a slight edge, the scientists say more research is needed, partly to figure out exactly how useful the improvements would be in the real world. Of course, there's a far more important issue at stake here: eating chocolate for science. Now that's my kind of research. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.